We just spent a lot of time working on figuring out how to count things. And we did that because this unit is about probability and statistics. And to be effective at computing probabilities, you need to be able to count things. So now that we're getting better at counting, let's talk about probability. From our textbook, we're told that probability is the measure of how likely an event is to occur. Each possible result of a probability experiment or situation is an outcome. The sample space is the set of all possible outcomes, and an event is an outcome or set of outcomes. Okay, so wait a minute. We just mentioned something called a sample space. I want to clarify this before we move on because sample space is going to be a big part of how we compute probability. So, depending on what the experiment or situation is, your sample space will be different. But the sample space is the set of outcomes for that particular experiment or situation. So for example, if we're rolling a number cube, like rolling a die, there are 6 outcomes. And the sample space would be a 1, a 2, a 3, a 4, a 5, or a 6. That sample space is the set of outcomes. There are 6 of those outcomes, but the sample space is the actual list of those 6 items. If we're spinning this spinner over here, it could land on red, blue, green, or yellow. So the sample space is red, blue, green, or yellow, and there happen to be 4 items in that sample space. So that was just me clarifying what sample space means. Let's keep talking about probability. First of all, I want to make sure you understand what probabilities look like. When we write probabilities, they're going to come in one of 3 forms. They might be a fraction, like 1 over 2, or they might be a decimal between 0 and 1, like 0.77, or they might be a percent between 0% and 100%, like 52%. So be ready to see probabilities in any of these 3 forms. For the most part, we'll start by just making fractions. Now we've talked about sample spaces, so let's just clarify what outcomes are. Equally likely outcomes have the same chance of occurring. When you toss a fair coin, heads and tails are equally likely outcomes. Favorable outcomes are the outcomes in a specific event. For equally likely outcomes, the theoretical probability of an event is the ratio of the number of favorable outcomes to the number of total outcomes. Now, there were a lot of words there. Again, I stole this from our textbook, but one of the key words that I want to focus in on is ratio, because ratio is like a fancy word for fraction. So essentially what we're going to do when we're making these probabilities, we're just going to be making fractions. Let me show you what I mean. The first type of probability that we're going to be computing is what we call theoretical probability. And as you can see, it's just a fraction. The notation that we use if we want to find the probability of a particular event is this P with the event in parentheses. So for example, if I want to find out the probability of a head when I am flipping a coin, I have to count the number of favorable outcomes. There's 1 head on a coin, and put that over the total number of outcomes in the sample space. And we just mentioned in the paragraph above that the sample space was head or tails, so that's 2. And so the probability of getting a head would be 1/2. Now remember, we might see that as a decimal, so that could be written as 0.5, or you might see it as a percent, which would be 50%. But this theoretical probability is originally created by making this fraction, favorable over total in the sample space. Let's look at some examples. Okay, in example 1, a CD has 5 upbeat songs and 7 slow ballads. What is the probability that a randomly selected song is an upbeat dance song? Okay, now remember we're making fractions, so the way we're going to write this problem out is we're going to start by writing our probability notation, P of the thing that we're looking for. We're trying to see if the song is upbeat, so P of upbeat. And on top of our fraction, we need to count the number of upbeat songs. There are 5. And then on the bottom of the fraction, we need to write down the total number of songs in our sample space. So together, the upbeat and slow ballads, 5 plus 7 equals 12. And so this is our probability, 5/12. Remember, the favorable or upbeat songs go on top, and the total in the sample space goes on bottom. I'm going to scribble that down here so you can't read it. Barely spelled the word space right. But I wanted to make sure you see that the way we find the probability of upbeat songs is put the number of upbeat songs, 5, over the total number of songs in our sample space, 12. The probability is 5/12. Okay. Here's a slightly more complicated example. A red number cube and a blue number cube are rolled. So basically a red die and a blue die. If all numbers are equally likely, what is the probability that the sum is 10? Okay, now we're going to see lots of problems where we're rolling dice. And so it's going to be good for you to have a picture of those outcomes handy. When we do our assignment, I'll have a picture of those outcomes on the page. Let me just bring up a picture right now, and we'll attack this problem. So here's a list of all of the outcomes when you roll a red cube and a blue cube. Okay? You might get a red one and a blue one, a red one and a blue 2, and so on. If you count all these up, there are 6 rows and 6 columns. There are 36 outcomes. So our sample space has a total of 36 outcomes. By the way, this picture, this is the sample space, the set of all outcomes. Now we are asked to find the probability that the sum is 10. So when I write this out in my notation, I'm going to write P, sum is 10. I'll put sum equals 10 just to use a little shorthand. And I've got to make this fraction. So I need to find out how many of these outcomes have a sum of 10. So as I'm looking through the list, I see that 6 plus 4 is 10, so that's 1. Ooh, there's a 5 plus 5, that's 2. And a 4 plus 6 is 3. Is there any other pairs there that equal 10? I don't see any. So when I make my fraction, according to my calculations here, there are 3 outcomes that are equal to 10. And remember, our sample space is 36, so my probability is 3 over 36. But this is driving me crazy. We always reduce our fractions, so this fraction reduces to 1/12. Right? You just divide both these numbers by 3, and you end up with 1/12. So the probability that we will get a sum that is equal to 10 is 1 out of 12, better known as 3 out of 36. Okay. For example 3, we have another slightly complicated problem here. What is the probability that a random 2-digit number is a multiple of 7? So we've got 2 things going on. We got to figure out what our sample space is first, and then we have to figure out which of those is a multiple of 7. So let's start with our sample space. Our sample space is 2-digit numbers. How many are there? Okay, well, I don't want to spend time writing all these out, so I'm going to think this through. If I counted all the numbers that are 2 digits, basically I would start at 10, and I would go from 10 to 19, and there are 10 of those. And then I would go from 20 to 21, and there are 10 of those. And I'd go from 30 to 31, and there are 10 of those, and so on. And the question is, where would I stop? I would stop at 90 to 90. I'm sorry. What a dingling. 10 to 19 was correct, but the rest of these are all wrong. I need to go from 20 to 29, 30 to 39, 40 to 49, 50 to 59. I'm just trying to count all these. And my last set would be 90 to 99. And there are 10 of those. So I'm going to have 10, 20, 30, 40, 50, 60, 70, 80, and 90. So there are 9 10s there. That means my sample space has a total of 90 numbers. Okay, that's our sample space. We have 90 of those things. Now let's talk about our favorable outcomes. Oops, I just slid the whole screen there, didn't I? Sorry about that. I'm going to put it back there. There we go. Okay, favorable. Those are multiples of 7. So basically, I just got to start multiplying numbers by 7. The first multiple is 1 times 7, which is 7. That doesn't count. So let's do 2 times 7, which is 14. 3 times 7, which is 21. 4 times 7 is 28. 5 times 7 is 35. 6 times 7 is 42. 7 times 7 is 49. 8 times 7 is 56. 9 is 63. 10 is 70. 11 is 77. 12 is what? 84. I'm just going to keep adding 7 until I get a triple digit. Then what? 91. And then 98. That's the highest to go. Once I get past there, I go into triple digits. So how many of those are there? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And so my probability of a multiple of 7 is going to be 13 over 90. Now, I can already hear some of you starting to get a little grumpy about this. I hate to tell you this, but a lot of the math that we're going to do is going to require some counting and some thinking and some patience, right? We're not just looking at a problem and automatically writing down the answer. That's not what this math is about. You have to have patience. You have to read the problem a couple times, consider what you're doing, and ultimately we need 2 things. We need a sample space so we can figure out what number to put on the bottom of our fraction, and we need favorable outcomes so we can figure out what number to put on top. This is a complicated problem. We had to count the 2-digit numbers, and then we had to figure out how many of them were multiples of 7. That's how you make this fraction. So be patient with yourself. Take the time to write out what you need to until you can count these things and then make the fractions. Now, I think you'll recall that we spent a lot of time figuring out how to count things, and we're going to need to use that when we compute probabilities, right? A mother is making different lunches for each of her 3 children. If each child grabs a lunch bag at random, what is the probability that all 3 children will get the correct bag? So again, first thing we need to do is figure out our sample space. And what I'm going to do is just do a quick little counting principle thing here to see if I can figure out what's happening here. So each event is just going to be the child grabbing a bag, right? When the first child comes through, that child has 3 bags to choose from. Once that person grabs a bag, there are 2 left for the next child, and then there's 1 for the final child. So that's a total of 6 outcomes. Basically, this is a 3P3 situation, right? We have 3 bags, and we're going to use all 3 of them, and the order in which the children get them matter. Okay, so that's our sample space. Now let's talk about the favorable outcomes. In this situation, we really just have to think about the favorable outcomes. So if she's only making 3 lunches, there's only one way for each child to get the correct lunch. And so rather than list out the possible favorables, I just have to say, oops, there's only one possible way. I just use a little common sense there. One possible way for all 3 of them to get their correct lunch. And so now we can write this probability. The probability that all are correct. Now spell that right. That's going to be favorable outcomes, which is 1, over the total outcomes in the sample space, which is 6. The probability here is 1/6. Okay, so we've talked about a few ways to figure out probabilities. Now I want to talk to you about something called a complement. So when you add up all the probabilities in a sample space, it has to add up to 1. And that becomes useful. Sometimes it's easier to count the things that don't happen than it is to count the favorable outcomes that you want to happen. And you can use that to help you compute probabilities quicker. Okay? And so the way we describe that is the probability of the complement happening. The probability of not event E is the same as the probability of 1 minus the probability of E. Let me give you a quick example here, and then we'll do a more formal example. So let's say we're rolling 1 die, right? And if I want to know what the probability is that the number is less than 6. An easier way to figure this out is to do 1 minus the probability that it is a 6, right? It's a 1 out of 6 chance of getting a 6. That means 1 minus 1/6 would be 5/6. And so that's a little bit easier way to count all of the probabilities that are less than 6. This is a simple example. It's really not that hard to count the 5, but for a problem where the numbers are larger, this complement will come in handy. So let me show you a slightly more complicated example. I don't know if you've ever played the game Battleship or not, but essentially what happens is the game is played with 5 ships on a 100-hole grid. Players try to guess the locations of their opponent's ships and sink them. At the start of the game, what is the probability that the first shot misses all the targets? So we want to know the probability that we're going to miss. Now, since there's only 5 ships on the game board, there are a lot of places where you can miss a ship, and counting all those would be a hassle. However, in this chart over here, we have the total for all the places where you would hit a ship, right? 2 plus 3 is 5, plus 3 is 8, plus 4 is 12, plus 5 is 17. So these are the 17 places where you would hit a ship. Did I add that right? 9 and 6, yep, 17. Okay, so what I'm suggesting is that we can use the complement here. We already quickly counted the possible ways to hit a ship. We should be able to use that to figure out how many, what the probability is of not hitting a ship. So let's say probability of miss, and instead of counting the misses, we're going to say that equals 1 minus the probability of hitting a ship, which we just calculated. So for us, that would be 1 minus 17 over 100. Now, that's the same as doing 100 over 100 minus 17 over 100, which is 83 over 100. So in fraction form, you'd say 83 over 100. A lot of times we'll write that as 83%. We have an 83% chance of missing on our first move in the game of Battleship. You've been very patient sitting through and listening to the video here, and we just have a couple of more types of probability to cover, and these are actually pretty easy. And then you'll get started on your own problems. So we already spoke about theoretical probability, and now we need to talk about geometric probability. Here you can see geometric probability is a form of theoretical probability determined by a ratio of lengths, areas, or volumes. In other words, it has to do with geometry. Let me show you what I mean. Okay, so example 6 here is about this picture with these semicircles. And the description is that there's 3 semicircles with diameters of 2, 4, and 6, and they're arranged as shown in the figure. If a point in the figure is chosen at random, what is the probability that the point is inside the shaded region? So this is kind of like a dart game, right? I'm going to throw a dart at this picture, and I want to know the probability that it lands in the purple instead of the white. So I'm making these little red dots to mimic that. Okay, first of all, we need to do some areas. So I'm going to do a little geometry calculation up here in the black space, and then we will make our fraction. So let's talk about the entire target here, the entire region. That is a semicircle. And you'll remember that the area of a circle equals pi r squared. Now we're not given the radii here. We are told the diameters. So we have to figure out the radii as we're doing these calculations. Let's do the whole entire circle first. So for the whole circle, the radius is actually 3. And remember, this is a half a circle. It's not a full circle. So we're going to do half of the area of a full circle with radius 3. So the full circle would be 9 pi centimeters squared. We need 4.5. For the whole picture, it's 4.5 times pi, and that's cm squared. Okay. Now, for the 4 centimeter circle, the radius is 2, and remember, we're doing half. So the full 4 centimeter circle would have a radius of 4 pi, which is 2 squared. But we need half of that, so that's a 2 pi. And then this little circle down here, this 2 centimeter circle, that has a radius of 1. The area of the full-size circle down there would be 1 pi, and we need half of that, so that's a half a pi. That's a half a pi. I just hit a weird button, so hopefully this comes out okay. So that's half pi centimeters squared. Okay. The reason I'm adding these things up is because to figure out the purple, I need to take the full and subtract these other ones. So I guess I'll do that right here. So purple. Purple is the full, which was 4.5 pi, minus the 2 smaller ones. So minus 2 pi minus a half pi. And so the purple ends up being a total of 2 pi. Okay, so what does that mean for us? Well, we're doing geometric probability. It's the ratio of the areas. So probability that we hit the purple, the shaded region, is going to be the favorable area, which is 2 pi, divided by the total area, which is 4.5 pi. And these are centimeters squared. Now, there's some math we can do here to make this answer a little less crazy. I'm going to cancel these pi's. And since I have 4.5 in the bottom, we usually don't like to write our fractions with decimals in them. So to get rid of it, I'm just going to double both numbers. And when I do that, I end up with 4 on top and 9 on bottom. And so the probability that I'm going to land in that purple area is 4/9. Okay, so these geometry problems, you're going to have to look up some formulas. I can help you with that. Don't panic. But we can do probability with geometry in the same way that we can do it with our experiments. So speaking of experiments, let's talk about experimental probability. Sometimes we're not figuring out in theory what might happen, but we're actually just reporting what did happen when we carried out experiments. And that's called experimental probability. We're still making fractions, but we just write down the fraction by counting the data that we're given. We're just reporting what happened. So it's the number of times the event occurred divided by the total number of trials. This one's pretty straightforward. Let me show you what I mean. Here in example 7, the data in the table is about a marble being drawn from a bag and then its color recorded in the table. So somebody already performed this experiment for us. They drew marbles out of a bag and reported what color they pulled. Our job is simply to find the experimental probability of drawing a pink or a yellow. And we do that in a very similar way to what we've done before. So our probability is pink or yellow. That's the event we want to check. So we just count these things. How many pink ones are there? There's 12. How many yellow ones are there? There's 12. So that's a total of 24. And how many total trials did we have? Well, we had 24 plus 10 is 34, plus 16 is 50. So 24 out of 50 is our probability here. Now remember, I'm a crazy math teacher, and I think we should always reduce fractions. So this is going to be a 12 out of 25, 12 over 25 for that fraction. Okay, so that's experimental probability, and really this is my favorite because all the counting has already been done for us. All we have to do is write the number down and make the fraction. I suppose I should have started with this example in the video so that you might think it's always this easy, but I guess I prefer to end with this just to show you that computing probabilities when you're doing experimental probability really is just a matter of adding up some numbers and making the fraction like we did here. Okay, that was a long video about probability. This is an introduction. You're going to work on some problems now, and you're going to get some right, you're going to get some wrong, you're going to make some mistakes, you're going to have some questions. That's all normal. You don't have to be perfect at it right now. Give it a go. You know you're making fractions. Write some fractions down, and then when I see you, we'll be able to answer questions, and if we need to, brush some things up and fix some answers, we can do that. Good work. Thanks for listening, and if you need me, you know where to find me. Take care.